Welcome to Study Loop.
Okay, why does a hexane not react with Br2? We get no reaction, that's what Nr means, or potassium permanganate, right? Why do we get no reaction? Well, the easiest way to describe this is to show this in contrast to a substrate which will react with Br2 and will react with potassium permanganate. Right, so the classic substrate that undergoes reactions with both of those reagents is an alkene. And if you'll recall, when we're talking about with Br2, what we've got is bromine that will act as both a nucleophile and an electrophile, and that a lone pair on bromine will attack the carbon while the double bond swings open to attack bromine, and additionally, the second atom of bromine will leave the Br2 molecule. But the meat and potatoes of the reaction that's going on is right here. How is this possible? Well, recall that bromine is really big, right? It's a big atom, and its electrons are rather diffuse, right? Far away from the nucleophile, right? And whenever we've got these big diffuse atoms, they can undergo what's called induced dipole, right? And they will spontaneously, on occasion, organize such that all the electrons will sort of shift to one side of the molecule, creating a negative side and a positive side. And in this way, bromine can act simultaneously both as an electrophile and as a nucleophile, and that's precisely what's happening here. This is the nucleophilic part of bromine where it's doing the attacking, but it's also being attacked. That's the electrophilic part of bromine. And so all that's happening when Br2 reacts with an alkene is that it is acting as both an electrophile and a nucleophile. Simultaneously, recall that sp2 hybridized carbons are somewhat positive, partially positive, or electrophilic in nature, right? Because sp2 hybridized carbons have greater S character to them, meaning the electrons are held closer to the nucleophile, or to the nucleus, right? But at the same time, when you've got a carbon-carbon double bond, recall that this is represented by the overlap of 2p orbitals, right? More accurately shown as the overlap of 2p orbitals forming a so-called molecular orbital. And that if you look at the region above a carbon-carbon double bond across the internuclear axis, there's actually an electron-rich region. Not actually multiple electrons in it, but in either case, carbon-carbon double bonds are simultaneously electron poor and electron rich, and as such, they can act as both electrophiles and nucleophiles simultaneously, much like bromine, but for a different reason. And we see this. This carbon is getting attacked. This carbon is doing the attacking, right? And so the way that hexenes or alkenes are able to, alkenes are able to interact with bromine gas is that they behave as both nucleophiles and electrophiles. Behave as nucleophile and electrophile. Okay, just like bromine. Now, if instead we consider hexane, right, recall that hexane is comprised entirely of carbon-carbon bonds and carbon-hydrogen bonds. Specifically, too, they're sp3 carbon-carbon bonds and sp3 carbon hydrogen bonds, and that the difference in electronegativity between each of these types of carbon or carbon and hydrogen is exactly zero for sp3 hybridized carbons and effectively zero for sp3 hybridized carbons and hydrogen. What this means is that this molecule is purely nonpolar, and unlike the case with our alkene, it has no electron-rich or electron-poor regions. Every one of these carbons is tetrahedrally coordinated, right? And there are no specific regions to any of these bonds that are electron poor or electron rich. They're effectively symmetric in all respects when it comes to electron density, right? So no electron rich or electron poor regions, and therefore they cannot act as nucleophiles or electrophiles. Right? And that's to contrast with, say, any kind of alkene. And just to drive the point home, right, the answer is the same for potassium permanganate as to why hexene reacts with it. Or sorry, any alkene will react with it. And that's that potassium permanganate exists as an ionic pair of potassium plus, which does not participate in the reaction, and permanganate minus. And our permanganate contains a nucleophilic oxygen and an electrophilic manganese, right? So in the same way, our alkene is able to react because it behaves as both a nucleophile and an electrophile, which is not possible for the nonpolar hexane.